Hello everyone. Thanks to everyone for watching this video. My name is Qidang. I am an architect and engineer. Today's video is titled Hemispherical Domes, and it is going to introduce the pressure surface in the domes. I'm going to give you an overview of what I'm covering in today's video. First at all, it is a bit of background to the topic, and then focus on the pressure surface and the minimum thrust for the hemispherical dome. Beautiful domes have been built firstly by Masonians and later by Romans and Byzantines. Domes were practically neglected in the Middle Ages, later rediscovered by the Renaissance and Baroque architecture. In this video, we will study the statics of the domes. First, we can see the dome membrane stresses. Initial membrane stresses occur in the dome's rotational shells. Later, the masonry dome probably cracks when the tension stresses in the hub rings near the spring, usually fading in the course of time. The initial membrane equilibrium is thereby lost, and the meridian cracks will arise and spread along the dome. The emergence of thrust is the main consequence of cracking of the hemispherical domes. For some simple dome arrangements, it is a relatively simple matter to obtain the analytical expression for the minimum thrust. By way of illustration, we will now analyze the case of a hemispherical dome with constant thickness without lantern. Consider the equilibrium of a small element of the unknown pressure surface to be determined. This surface has a regular rotational shape and runs continuously between the dome extradoors and intradoors. We define the unit load G per mean surface of the dome. Approximately the same load G will act on the unknown surface. This figure shows an element, dA, of this pressure surface. The force and phi are the only ones applied on this element. Equilibrium of the element along the y direction gives this expression, where the ring radius r and the curvature radius R of the meridian refer to the unknown pressure surface. Then we get this equation. Equilibrium of the element along the z direction normal to the pressure surface is instead expressed by this equation. After simplification, we have this expression. Combine the two differential equations of equilibrium, then we obtain this equation. Now we can create an equation and know r times R times cosine phi square is a constant. By looking at the equilibrium condition along the horizontal projection of a slice element of magnitude d theta, we can explain the significance of this condition. From the figure, we have this equilibrium equation. After simplification, we have this expression. Because n phi equal to g times R times cosine phi, the equation becomes this expression. Thus, we derive the condition on the slice of unit magnitude theta equal to 1 rad, so that g times r times R times cosine theta square equal to h. Now we can draw a coordinate system of r and z. From the geometry of the figure, we can write r times dr equal to c times d phi over cosine phi. By integrating this equation, we can obtain this expression. Then we can create an equation for the mathematical derivation. Because tangent theta is equal to dz over dx, we get this equation. Using the hyperbolic function sin x, and taking into account that z equal to 0 at x equal to 0, then c1 is 0, so we finally obtain here. This equation defines a family of pressure surface, each one corresponding to a particular choice of the constant c. Among these, we have to choose that corresponding to the minimum thrust. Now we can try to find the pressure surface of the hemispherical dome in an admissible equilibrium state. At the meridian cracking of the hemispherical dome, thrust takes place. The supporting structures, as the drum, will deform and a small widening of the dome springing occur. The dome adapts itself to the settlement, and the minimum thrust state develops in it. This state is so characterized that the thrust surface is all contained inside the dome, and the extra doors and the inner doors of the dome will be touched by the thrust surface along two circles corresponding to the two internal hangings of the settlement mechanism. This figure shows the two hinges of the mechanism form at points M and N. Suitable conditions will define the position of the pressure curve in the slice. The pressure curve will be tangent at points M and N, respectively at the extra doors and at the inner doors of the slice. We have the two equations. If capital R is the mean radius of the dome and T is thickness, we have R1 and R2 equations. Thus, we can derive the mathematics to obtain the new conditions of R1 and R2. Finally, we obtain the following expressions of R1 and R2. The same constant 2c is contained in the two conditions. For the sake of simplicity, we set chi equal to T over 2R. Then we have the equation of 2c. The condition is one of the two equations required to obtain the angles phi1 and phi2. Now we consider the other two conditions, those prescribing the pressure curve through the points M and N. We have ZR1 and ZR2. The same constant A is contained in the two conditions. This equation is together with the equation of 2c, and is required to obtain the two unknowns phi1 and phi2. Now we will use these equations to find the minimum thickness of hemispherical dome. Let us assume that the pressure surface touches at the base the extra doors of the dome. Let us admit this condition, from which we can evaluate the corresponding chi minimum. We also show the constant C and A equations from our previous description. To maintain the pressure surface within the slice, the settlement mechanism cannot admit a hinge at the dome zenith. Here we have Z0 equal to A. The constant A defines the position of the pressure curve at the zenith, so that the value of A should be less than the dome thickness T. The solution angles phi1 and phi2 represent the real positions of the internal hinges of the pressure curve at its state of minimum thrust, must satisfy the compatibility conditions at the zenith and spring-ends. Search for the minimum thickness of the dome. The thickness can be reduced as far as the pressure surface that goes up from the spring and passes through the defined points M and N, touches the inner doors at the zenith. The minimum thickness ratio can be obtained under the condition that, at the zenith, we have T minimum equal to 2 times chi minimum times capital R. Combine these equations, we obtain chi minimum is 0.0226, phi1 is 31.618 degree, phi2 is 69.038 degree. Thus, the minimum thickness ratio should be equal to 0.0452. This figure shows the pressure curve in the minimum thickness dome. We can notice that at the springs, the pressure passes barely within the dome. Any further thickness reduction pushes the pressure curve downwards, outside the crown. The ratio T over R equal to 0.0452 thus represents the minimum thickness of the dome. From conclusions, what we learned? The hemispherical dome is a surface formed by the rotation around the vertical axis of a semicircle. It has a circular basis and horizontal sections, and are a type of circular dome for that reason. In an admissible equilibrium state, the thrust pressure surface should be inside the dome. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative, and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.